Welcome everyone to Gradient Daily. I'm absolutely thrilled to have you here today because we are embarking on a really serious graduate-level deep dive into what I can only describe as an absolute paradigm shift in computer vision. Today, we are meticulously unpacking a groundbreaking archive paper. It's titled Grounding Image Matching in 3D with MASt3R, and it's brought to us by researchers Vincent Leroy, Johan Cabon, and Jerome Rayvad. Now, listen. For anyone working in spatial computing, robotics, autonomous navigation, or even augmented reality, you know that image matching is the beating heart of your entire pipeline. It's literally how an AI understands that, say, the corner of a building in one photograph is the exact same physical corner in another photograph, even if that second photo was taken from a wildly different angle or under totally different lighting. But here's the thing. For decades, the entire field has been approaching this exact problem with a massive fundamental blind spot. We've been constrained by legacy architectures that just don't capture reality. Well, this research paper completely rewrites the mathematical rules of that approach. In this explainer, we are going to break down the actual network architecture, the specific dimensionalities of their feature descriptors, the mathematical bottlenecks they completely shattered regarding matrix multiplication, and the astonishing empirical results they achieved out in the wild. This is a comprehensive PhD-level analysis of a true leap forward in visual style and geometric understanding. So get ready, grab your notes, we're in for a masterclass.
Okay, let's dive right into this because this quote right here, which is pulled directly from the very beginning of the paper's abstract, is the crux of their entire argument. The authors boldly state, despite matching being fundamentally a 3D problem, it is typically treated as a 2D problem. Now, it sounds almost too simple when you just read it out loud, right? But the algorithmic implications of this single sentence are absolutely massive. I mean, think about traditional feature matchers or early convolutional neural networks. How do they see the world? They look at flat two-dimensional grids of pixels. They calculate gradients. They map color histograms. They look at 2D spatial frequencies. But the physical world we actually live in isn't a flat grid of pixels. When a camera captures an image, it is performing a perspective projection. It's taking a deeply complex, three-dimensional spatial reality and flattening it onto a two-dimensional digital plane. By treating image matching purely as a 2D mathematical exercise in pixel space, historical AI pipelines have literally been throwing away the single most critical piece of context, the underlying spatial geometry of the scene itself. The authors here are arguing that this historical precedent isn't just a slight inefficiency. No, it is a potentially hazardous architectural choice for the future of any robust AI vision system that actually has to operate in the real, three-dimensional world.
To truly understand how this paper solves that historical problem, here is our syllabus for today's masterclass. We'll start with the 2D-3D matching disconnect. Then we'll cover DUSt3R and Pointmap regression. Third is the MASt3R architecture itself. Fourth, solving that tricky quadratic matching complexity. Fifth, we'll dive into the map-free localization results. And finally, we'll wrap up with a critical discussion on the future of these models.
All right, moving right into section 1, the 2D-3D matching disconnect. Let's really unpack why we desperately need to move beyond standard two-dimensional pixel fields. To make the mathematical shortcomings of those traditional 2D models incredibly intuitive, let's use a very concrete visual analogy. Imagine you are given two flat-printed photographs of a highly complex statue. Let's go with Michelangelo's David. One photograph is taken straight on, perfectly from the front. The other photograph is taken from the side, looking up at a very sharp, awkward angle. Now, your task, or rather the AI's task, is to perfectly align specific microscopic points between these two images, like the exact tip of the nose or a specific curl of hair. If you are only looking at the 2D visual patterns, the flat shadows, the 2D shapes, you are going to struggle immensely. Why? Because that side view geometrically distorts the shapes, the lighting completely changes the pixel intensity values, and crucially, parts of the face that are clearly visible from the front are entirely occluded or hidden from the side view. You are essentially trying to guess the volume of a complex three-dimensional object based purely on a couple of flat two-dimensional shadows. And this is exactly what classical feature extractors like SIFT or standard convolutional neural networks have been forced to do for years. They do not natively encode the fact that the statue actually has depth. They are only encoding localized spatial frequencies and flat pixel gradients. It's a fundamentally flawed way to understand physical space.
So the crucial takeaway here is this fundamental difference in paradigms. On one side, we have traditional 2D pixel fields. This approach matches visual patterns on a flat plane. Let's look at this through the lens of a standard CNN. A typical convolutional neural network uses tiny sliding computational windows. Usually these are 3x3 or 5x5 pixel kernels that just scan across an image.
These kernels are desperately trying to learn local textures and edges. But here's the catch. They lack inherent rotational invariance and scale invariance. More importantly, they operate purely in what we call camera space. If the camera angle drastically changes, the 2D visual pattern warps way beyond what that little kernel can recognize. It just fails. On the flip side, we have the 3D geometry-aware approach. This paradigm matches points based on absolute spatial reality. It understands that a pixel isn't just an RGB color code, it actually represents a specific physical coordinate, an exact X, Y, and Z location in world space captured by a ray of light intersecting a camera sensor. If your AI understands the actual 3D geometry of the scene, it doesn't get confused when the camera suddenly swoops to a radically different perspective. Why? Because the physical coordinates of that statue in world space haven't moved a single millimeter. Only your viewpoint is changed. Grounding image matching in 3D is all about giving the neural network absolute spatial awareness, completely freeing it from the fragile, warped distortions of 2D camera space.
And that brings us seamlessly to Section 2, where we need to analyze the foundational architecture that actually made today's breakthrough mathematically possible in the first place. Let's talk about DUSt3R and the deep learning concept of point map regression.
Before we get into the really heavy network architecture, let's ground this with another everyday visual example. Think back to those classic 3D pin art toys you might have played with as a kid. You know, the ones with thousands of little metal pins encased in a plastic frame. If you press your hand into the back of it, the pins push forward and they create this perfect, dense, physical topographical map of your hand in 3 dimensions. Every single point on your hand now has a corresponding pin that represents its exact depth and its exact position in space. Well, this is precisely what we want our AI to do to a flat 2D photograph. We want the network to take a flat matrix of pixels and mathematically push them out into 3-dimensional space, transforming a completely flat sheet of digital glass into a rich, topographical, spatial reality. It's a beautiful concept when you really picture it.
In the realm of highly advanced computer vision, this pin art process is formalized mathematically through a process called point map regression. The MASt3R paper we're discussing today builds directly upon a very recent, highly powerful 3D reconstruction framework called DUSt3R. Now, DUSt3R is a vision transformer-based method. It maps 2D pixels directly to dense 3D spatial coordinates. The term regression here is absolutely vital for you to understand. It means the neural network isn't just classifying a pixel as, belonging to a car or a tree. Instead, the network is predicting continuous, highly precise numerical values for the exact X, Y, and Z physical coordinates of every single pixel in the entire image field. Now, you might be wondering why use a transformer instead of the standard CNNs we discussed earlier. Well, it comes down to a property called the global receptive field. In a transformer architecture, mechanisms called self-attention allow the network to calculate relationships between every single pixel and every other pixel simultaneously. A patch of pixels in the top left corner can directly communicate with a patch way down in the bottom right corner, mathematically weighing their relevance to one another. This global context is absolutely mandatory for accurately inferring underlying 3D structure from a 2D image, because geometry is inherently defined by wide-scale spatial relationships, not just tiny, isolated 3x3 local textures.
Now let's be clear, DUSt3R was an absolute revelation for the field when it dropped. But as a precursor to today's paper, we have to evaluate its performance profile critically, because it uses those self-attention mechanisms to inherently understand 3D space globally. DUSt3R demonstrated unprecedented robustness to extreme viewpoint changes. I mean, you could feed it 2 images taken from wildly different, completely unconstrained angles out in the wild, and its fundamental understanding of the scene's macro geometry wouldn't break down. It conquered difficult visual perspectives that literally shattered older models. However, the authors of the MASt3R paper identified a critical bottleneck here. While DUSt3R was undeniably robust in a broad macro sense, its overall matching accuracy for microgeometry was actually severely limited. It could generally figure out the overall shape of the room, right? But when you asked it to match a very specific subpixel point from image A to exactly the corresponding subpixel point in image B, it just lacked the microscopic precision required for high-end downstream tasks. We're talking about things like autonomous driving or high-precision robotic manipulation. It was a classic architectural trade-off. You got immense structural robustness, but insufficient fine-grained accuracy. DUSt3R, in a way, represented a false summit in the long climb toward perfect 3D image matching.
And that leads us directly to Section 3, which is the absolute core of today's deep dive, the MASt3R architecture and its generation of high-dimensional, dense features. This is exactly where the authors detail their precise architectural breakthrough to conquer that false summit we just talked about.
Let's meticulously walk through the actual architectural data flow of MASt3, treating this like the graduate-level schematic that it is. Step 1. The system ingests two completely distinct viewpoint images of the same environment. Step 2. These images are processed through the powerful vision transformer base known as a Viety encoder, which they purposefully inherited from DUSt3. This base network crunches the global context via those self-attention layers and begins regressing the 3D point maps, the actual spatial coordinates. But here, right here, is the critical architectural intervention in Step 3. The authors did not just rely on the point maps. They ingeniously augmented the network by branching off a completely new parallel output head. Instead of just outputting the physical XYZ coordinates, this new head applies a series of dense layers to simultaneously output what are called dense local features. Specifically, the network generates a high-dimensional vector. We're talking about a 256-dimensional numerical descriptor for every single pixel in the image. I want you to think of this 256-dimensional vector as an incredibly complex mathematical cryptographic fingerprint for that specific physical microscopic point. And finally, Step 4, during training they apply a highly specific additional matching loss directly to these fingerprints.
And this brilliantly illustrates the elegance of modern neural network loss design. Let's dig really deep into that Step 4 I just mentioned, the additional matching loss. In deep learning training, a loss function is basically the mathematical penalty applied to the network when it makes a mistake. It calculates the error gradient so the network can mathematically adjust its internal weights via backpropagation. Well, the authors introduced a totally new training objective based on contrastive learning principles, specifically tailored for those 256-dimensional dense local features. This matching loss function operates entirely in high-dimensional latent space. It strictly calculates the cosine similarity, or the Euclidean distance, between the mathematical fingerprint of a physical point in image A and the fingerprint of that exact same physical point in image B. If they are the same physical point in the real world, the loss function brutally penalizes the network if those 256-dimensional vectors aren't nearly identical. Conversely, it forces the network to mathematically push the vectors of different physical points as far away from each other as possible in that latent space. By forcing the network to minimize this specific contrastive loss, MASt3R learns to generate hyper-accurate, totally distinct features that are mathematically invariant to lighting, to scale, and most importantly, to camera angle. It forces microscopic pixel-to-pixel accuracy. It's brilliant.
But listen, a highly accurate, high-dimensional architecture means absolutely nothing if the computational overhead totally freezes your hardware. So let's transition to Section 4, solving quadratic matching complexity, and see how they algorithmically overcame the fundamental mathematical bottleneck of dense feature matching.
To really grasp why feature matching is such a massive computational hurdle, we need one more analogy. Imagine you're at a large corporate networking event, and there are exactly 1,000 attendees. Now imagine the organizers institute a strict, unbreakable rule where every single person in the room is required to formally shake hands and exchange a business card with every other individual person in the room. Person 1 has to shake 999 hands. Person 2 has to shake 999 hands, and so on. The total number of handshakes explodes exponentially. It would take hours, the room would freeze in absolute gridlock, and nothing else would get done, right? Well, this is precisely what happens inside a GPU during dense image matching. When MASt3R outputs those 256-dimensional fingerprints for every single pixel, it means you have tens of thousands of vectors. If you want to match image A to image B, comparing every single feature vector in image A to every single feature vector in image B requires calculating the dot product for every possible pair. The sheer volume of matrix multiplication required is astronomical.
In theoretical computer science, we express this nightmare scenario using big O notation, specifically OFN², which denotes quadratic complexity. If n represents the number of pixels, the computational cost and the memory requirements scale by the square of n. Let's do the math out loud and put real numbers to this. If your image has a relatively modest 100,000 pixels, well, n² means your hardware has to perform 10 billion, with a B, 10 billion high-dimensional vector comparisons just to match two single frames. If you decide to double the resolution of your images to get a clearer picture, say 200,000 pixels, your computational load doesn't just double, it skyrockets to 40 billion comparisons. For real-world downstream AI applications, like a drone trying to rapidly navigate through a dense forest at 60 frames per second, or an augmented reality headset trying to instantly map your living room geometry as you move your head, an OFN² bottleneck is an absolute death knell. The GPU's memory bandwidth simply cannot process the dense matrix multiplications fast enough. The system will hit severe thermal throttling, it will lag, and ultimately, it will crash.
So the researchers faced a seemingly insurmountable algorithmic wall here. Think about it. They had successfully built an architecture that is incredibly robust in 3D and incredibly accurate on a microscopic level thanks to that new dense feature head and contrastive matching loss we talked about. But it is practically unusable in the real world because of the sheer volume of matrix multiplications required. This brings up the absolute most critical question of the entire paper. How do we accelerate this massive computational load without taking naive shortcuts that would destroy the strict theoretical guarantees of accuracy we just fought so hard to build? You can't just randomly drop pixels to speed things up, right? Because then you ruin the precision.
So let's look at how this builds into their definitive algorithmic breakthrough. The authors introduced a novel, highly optimized mathematical scheme that they call fast reciprocal matching. Now the key word here is reciprocal. For a match to be considered mathematically valid by the system, pixel A in image 1 must identify pixel B in image 2 as its absolute closest mathematical neighbor in that high-dimensional feature space. But that's not all. Pixel B must simultaneously identify pixel A as its closest neighbor back. It is a strict two-way mutual handshake. But here is the absolute genius part of their implementation. Instead of calculating the entire brute force ON² pairwise distance matrix to find these neighbors, which we know crashes the system, they implemented a highly optimized symmetric filtering process. This process utilizes advanced nearest neighbor approximation techniques and dual softmax constraints to compute these mutual nearest neighbors directly. This elegantly completely bypasses the need to hold a massive dense matrix in the GPU memory. The result? It accelerates the matching processing by literal orders of magnitude. But wait, it gets better. The truly masterful part of this algorithm is that by strictly enforcing this reciprocal mathematical constraint, they effectively filter out a massive amount of structural noise and false positive matches. So this fast scheme didn't just speed up the inference time of the network, it actually acted as a structural regularizer that yielded significantly improved matching accuracy. I mean, it is a rare, flawless win-win in modern algorithm design.
With the dual-head architecture built, the loss function mathematically tuned, and that fatal O of n² quadratic bottleneck completely shattered, it was finally time to put MASt3Rs to the test against the absolute bleeding edge of the field. Let's analyze Section 5, the map-free localization dataset results.
To truly understand the gravity of these empirical results, you first have to understand the sheer rigor of the test itself. The authors evaluated MASt3R on the map-free localization dataset. In modern computer vision, this is notoriously one of the most hostile, unconstrained tasks imaginable. Here's how it works. You are given a query image taken somewhere out in the wild. The neural network then has to calculate the exact 6 degrees of freedom camera pose, meaning the precise physical XYZ coordinates and the exact rotational pitch, yaw, and roll angles of where the camera was located using only a single reference image. No GPS data, no pre-built LiDAR maps, just raw pixel data. To score this, the industry relies on a metric called VCRE-AUC. This stands for Virtual Camera Relative Pose Error Area Under the Curve. Now, without getting completely lost in the calculus, VCRE-AUC is an incredibly stringent, unforgiving metric that measures the area under the error curve against the absolute ground truth. If your 3D geometry estimation is off by even a fraction of a degree, your VCRE-AUC score completely tanks. It is the definitive metric that separates academic, laboratory toys from industrial-grade robotic tools.
Now, what is truly mind-blowing about these empirical results is the sheer magnitude of the leap. When evaluated on this brutally difficult map-free localization dataset, MASt3 didn't just edge out the competition by a slim margin of error percentage. As we look at the data here, it beat the absolute best previously published state-of-the-art methods by a staggering 30% absolute improvement in VCR-AUC. I really need to emphasize the word absolute here. In the hyper-competitive field of AI research, teams from top universities will literally fight tooth and nail for months just for a 1 or 2% relative improvement. To achieve a 30% absolute leap on a geometric metric this stringent is practically a generational jump. It definitively, empirically proves that natively grounding your image matching in a 3D transformer framework, augmenting it with high-dimensional dense features, and solving the algorithmic complexity yields a dramatically superior mathematical understanding of spatial reality compared to traditional 2D pipelines. However, as rigorous academics, we cannot just look at the high scores on a chart, declare total victory, and call it a day. Let's transition into our final section, Section 6, Critical Discussion and the Next Steps in 3D Vision. Let's impartially evaluate this paper's core assumptions, like we are sitting on a PhD defense committee.
Objectively dissecting the MASt3R framework, the architectural strengths are undeniable. The fast reciprocal matching algorithm successfully provides orders of magnitude faster inference, completely solving a fatal, long-standing flaw of dense feature matching. Furthermore, by building on the DUSt3R transformer foundation, it successfully retains that highly sought-after extreme viewpoint robustness. However, we must impartially note the strict mathematical limitations here. Because MASt3R relies on the base Pointmap regression of DUSt3R, it inherently inherits its underlying assumptions about scene physics. For example, Pointmap regression typically assumes relatively rigid static scenes. If you point this specific architecture at highly transparent surfaces like massive glass facades on a skyscraper, or deal with massive specular reflections like a rippling body of water, or wildly dynamic, fluid environments, the transformer's self-attention layers might seriously struggle to accurately regress the true underlying 3D spatial coordinates because reflections move depending on perspective, right? The most critical future test for this architecture will be deploying it into real-time mobile AI hardware. Running a vision transformer that outputs 256-dimensional vectors per pixel requires massive memory bandwidth. Can we quantize and compress this heavy network enough to run natively on a smartphone's neural processing unit without triggering severe thermal throttling and just burning through the device's battery? That physical hardware constraint is absolutely the next frontier for this research.
All right, let's lock in the knowledge. Here are your 3 memorable takeaways from today's masterclass. Number 1. Image matching is intrinsically a 3D spatial problem. Continuing to treat it with flat 2D pixel field kernels severely constrains the potential of autonomous computer vision. Number 2. The MASt3R architecture brilliantly solves this by taking the 3D point map regression of a vision transformer and adding a parallel dense feature head, generating high-dimensional descriptors trained with a specific contrastive loss to guarantee microscopic pinpoint accuracy. And number 3, the implementation of fast reciprocal matching successfully breaks the O(n)² quadratic bottleneck through symmetric nearest neighbor filtering, resulting in an algorithmic framework that is highly efficient and yields a massive 30% absolute performance boost in state-of-the-art spatial mapping.
You know, the MASt3 paper isn't just another iterative software update. It forces us to ask a deeply provocative question. If we've been mathematically processing visual data fundamentally wrong for the last 20 years by trapping it in flat camera space, what other deeply ingrained flat assumptions and artificial intelligence are just waiting to be pushed into the third dimension? We are literally witnessing the geometric foundation of spatial computing being rewritten right in front of us. Thank you so much for joining me for this comprehensive graduate-level deep dive here on Gradient Daily. If you found this breakdown valuable, please do smash that like button, hit subscribe, and ring the notification bell so you never miss out on the absolute cutting edge of AI research. We are here every single day decoding the architecture of the future. I'll see you back here tomorrow for another masterclass. Keep learning.